So my name is Jeff Muller. Welcome today to the Introduction to Software Engineering. This is intended for non-ICT specialists. I am a technical coordinator for the Human Brain Project at the École Polytechnique Fédérale de Lausanne. In this course, we're going to try to address some of the issues in software engineering which are probably most relevant to non-ICT specialists. Almost everyone these days, if you are a technician or a scientist, will be interacting with a large-scale software project at some point. And it's important to understand that many of the aspects of software engineering that are going to affect you most are going to be those that are related to project management. But it's also useful to have some awareness of what software development or the development of a product actually looks like. So in principle, we're going to try to address a really rough overview of what software development is. What makes software development estimation hard? So some key factors. Obviously, we're not going to be able to cover everything, but we will cover some of the key factors. What is software project management, and how does it attempt to make software projects predictable? And we'll try to address some limitations of these approaches. This text, the presentation is primarily focused on concepts that are presented in a classic software engineering textbook called the Mythical Man Month. A lot of these practices have proven themselves time and time again. There are new ideas that have developed since then, but in principle, large quantities of the insight that can be gained from this book are still applicable today. So let's start first with what I would consider one of the root causes for the fallibility of prediction when it comes to a software project. So there are definitely limitations to the human brain. The human brain is not a computer. And when we try to do certain tasks which would be trivial for a computer, we can kind of highlight some of the limitations. This is a task that was given to an intern by a psychologist. The article is linked at the bottom of the screen. And it's a common test that is given to try to highlight some of the fallibility of human memory. So the task is actually to draw a complex object from memory, in this case a $1 bill. Everybody's highly familiar with this if you live in the United States. You could do the same test here with a euro, for example. You can see that this is recognizable as a dollar bill, as a piece of currency. It has some key factors which make it recognizable in this sense, but it actually doesn't have very much detail. And what's interesting about this is that this is a repeatable event. Most people can't actually recall or perceive the pieces that are missing from the dollar representation that they're trying to recreate. When they do the same task with a dollar bill present, we get a fundamental difference in the level of detail. And this kind of highlights that while the human can actually perceive some of these details and can be aware of them when it's sort of right in front of them, it's highly difficult to do this over an extended time frame. And so unless you're looking right at the dollar bill, it's quite difficult to actually recreate some of the important details. And so this actually has some pretty significant implications for software engineering. This limitation of memory and state awareness has huge impacts on programming, debugging, testing, designing, and planning. And as a result, humans have a limited ability to predict delivery of software on time and on budget. And also, it's a similar issue, but typically many software projects fail because they didn't intend to build the right thing, and a similar process is in place that keeps us from being aware of the design space for the problem. The result is that failure in large-scale ICT projects is actually quite common. If you do a Google for failed software projects, large-scale or otherwise, you can find many, many, many lists. They cover everything from government projects to private projects. The criteria for a failure is quite diverse, but it is a well-studied problem, and there's quite a lot of documentation from reputable sources that describe what can be considered a failure, what the cost to society for such failures are. But it is extremely significant. Anytime you hear about a software bug on the news that is responsible for security flaw, if it's made in the news, it probably has a significant impact to society, and it's important to be aware of why these things occur. It's not because typically some programmer just forgot, was too lazy at some point in the process. So before we go any further, I should try and give you a little bit of a basis on what it takes to develop a product. Now, this is a very high-level view. I'm trying to present a view that is amenable and understandable to someone who hasn't been part of this process. If the expert practitioners will look at this and say that I'm missing key steps, but in principle, all of these steps would be necessary to produce a software product. First off, you typically need to identify what your program is supposed to do and what it's and who it's supposed to do it for. Even in the sense where you're doing a scientific piece of software, you're typically benefit if you can identify a customer, even if they're not paying you for it explicitly. You want to try and do some sort of design phase where you're trying to understand the problem and how your program will actually solve that problem. Very important, and this is often actually skipped by people who are doing software development, especially those that are less experienced, is you need to decide how you're going to test that the program is doing what you think it should do. This is typically called a testing plan, but it's a fairly non-trivial operation, and it requires quite a lot of understanding of the problem you're trying to solve. You need to program it. This is what's typically called software development, but in principle, all parts of this are actually under the umbrella of software development. The programming part is the part that gets the most attention in general. I'll talk a little bit more about that in following slides, and I'll relate that a little bit to debugging. So debugging is the process of actually looking at your program, looking at the source code for it, looking at its behavior, and trying to really understand where it's doing something that you don't expect. The typical terminology for an unexpected effect is a bug, and these can have sometimes disastrous results from a security standpoint. If in critical control systems, it can actually result in people's death. So obviously, you want to have a program that's bug-free. When you actually are getting ready to provide this to customers, you typically need to provide some sort of documentation, be it video documentation. You need to help people use it. Typically, a software program is complex enough that you can't just pick it up off the shelf and use it. And in general, making things easier is also more expensive. So sometimes it's better to invest in documentation than making a program easier to use. Testing is really key. It's part of the debugging process in a sense, but it's also part of your validation process to make sure that what you produced is something that you can actually offer to your customers. Once you have something that you're comfortable with, you can deliver it to the customers. This is I won't talk about this too much, but there's also a body of knowledge here with respect to how you interact with the customers when you're delivering products, what information they need, how you engage them around these ideas. You will almost always have to have some level of support. So it doesn't matter how great your product is, people will always have trouble using it. And it might not be because of your fault, it might not be their fault. Just assume that you'll have to do it and assume that you will need somebody to help people use your software. After you've actually delivered your software, you will find new bugs if you're paying attention, if you're working with your customers. In this case, you actually will need to repeat this process again. You go back to 5, you debug it, if you're lucky, you have enough money to add features, and you go through this process again of re-releasing software with fewer bugs. This is kind of based a little bit around a model where in a business where you actually still collect money somewhere along the line. In scientific software, it's similar, but that the funding is a little bit more indirect through a part of a research program or some request from a research program. So programming. I'll try to boil this down as much as possible because this gets quite jargony quite quickly. So in a sense, programming is the attempt to try to teach or explain to a computer how to perform a complex task. This can be quite challenging because computers are 100% explicit in the execution of their programs, and so the instructions have to be complete and they have to be precisely specified. Going back to the dollar bill experiment. This is the human limitations make this a really non-trivial exercise. Your ability to perceive extremely complex objects is limited, and this has implications for how reliable you are going to be in teaching a computer to do this kind of task. In the early days, programming was sort of, let's say, a very special exercise. Initially, programming was done with machine code. This is virtually unusable by humans. Typically you have very specialized people that have a very specific interest in dealing with really complex systems and precise minutiae and trivia, who will go in and actually sort of initially flip the bits on an Altair, for example, to enter the opcodes. This is, it still has an application today in a sense because these opcodes are actually the instructions that your computer central processing unit executes. Each type of CPU uses different opcodes, which is why you can't run the same software on your laptop that you run on your phone, at least in part. Now, once people got sort of fed up with the limitations of what they could do when they were entering machine code directly, they actually moved on to something called assembly language. And assembly language made this somewhat better. You can see on the right-hand side, I'll give you a little bit of an outline here of what you're seeing on the left-hand side versus the right-hand side. This is somewhat easier than machine code, but it's still quite challenging. It's virtually impossible to build large complex systems with assembly language alone. And what I would say here is that on the left-hand side, you see a collection of hexadecimal base 16 numbers. And on the right-hand side, you see a collection, you see a number of columns here. You have the opcodes here in the center and the assembly language mnemonics in this line here. And the idea here is that certain collections of opcodes are associated with something that humans can remember slightly better. But this is still a very specialized operation and is extremely error-prone and time-consuming. So software engineers, in an attempt to try and make these types of issues more, to make these types of problems easier to solve, to try and increase their ability to express high-level ideas to a computer, invented something called a compiler. High-level compiled languages make this a little bit easier. Some common examples that are in heavy use today are C, C++, and Java. There are many other examples, but we'll focus on these ones because they're quite the most common. Basically what happens is a human produces a human-readable piece of text file, and this is actually fed to a special program called a compiler, and the compiler translates this into machine-readable code. There's some caveats here. Sometimes they run on real machines, sometimes they run on virtual machines. It's not a significant difference, but Java is slightly different from C++ in this respect. Now, what's important, there's a little a snippet of code here it gives you an example of what Java code looks like. Typically, it's much easier to express complex ideas here than it is to express them in assembly language. That said, it still requires a fairly high degree of skill to be highly productive in such a system. There are many caveats. There are many patterns that are used to actually communicate ideas between programmers, and these play a key role in the body of knowledge that is needed to actually build larger scale systems with these types of languages. A large portion of the software development community has moved on and started doing a lot more work in things called interpreted languages. And the idea here is that you have the code that runs inside of a special program called an interpreter, rather than being compiled into machine-readable code. And these languages have the upside that they're typically easier to learn and express complex ideas. So they're a little bit more human-friendly in a sense of the way that you describe your problems. The result is that you have shorter development cycles and they're typically highly productive. It's not all positive though, because in this case, your programs run slower. This can be a problem or not a problem. A good programmer can work well with these trade-offs. Some examples that you might be familiar with if you are involved in scientific software development or web software development. Python is very common in the web and scientific development. It's very popular in the Human Brain Project and in many scientific disciplines. Ruby is very common in web development. PHP is very common in web development as well. And R is another notable one, which is very popular for statistics analysis. So if you're sort of on the periphery of statistics or machine learning, you're probably familiar with this system as well. And you can see here on the right-hand side, this is a chunk of Python code from an application inside the Human Brain Project. It may be a little bit difficult to see the difference between this one and the previous example, but in principle, these types of programs are much easier to understand from a human standpoint than a C++ program. Now, it's important to note that even after we've written our software, this is actually just a really small part of the whole process, and programs always need to be tested. It's basically impossible to write a program and not have it have bugs the first time around. So you will need some testing to make sure that they are functioning as expected. So when testing will almost always reveal unwanted or unexpected behavior. These are called bugs. This requires one to debug the program, identifying the cause of the bug and modifying the program to remove the bug. This is a bit of a problem because any change to the software can actually introduce new bugs, and so then you are required to retest. And then if you find any new bugs at that point, you revisit this problem and you debug it, you make some changes. The change potentially introduces new bugs, and you continue this process until you're comfortable that the program is stable and well behaved. This seems a little bit maybe challenging in a sense, but actually good programmers can typically provide decent estimates for working programs that would be the output of this process. They do it because of experience with the complexity of certain problems, and generally they can give you a reasonably good estimate of a working program in X amount of time. But this is actually quite a bit different from a product. So a program is usable to the programmer who produced it. A product is something different. That's something for someone else. And in this sense, you need some additional pieces. You need documentation, which is going to be part of your support activity. You're going to need much better testing, and you're going to need more debugging, obviously, because better testing is going to lead to more problems. And according to the Mythical Man Month, a product will take roughly 3 times the amount of time it takes to produce a simple program. And so this is a little bit problematic because most programmers think in terms of the program development time when they provide their estimates, but the product time is typically much longer. So individual tasks can be very predictable, as we kind of outlined in this simple program example. But as the project scope grows, the temptation is to add team members to increase productivity, to reduce the amount of time that it takes to deliver a piece of software. Many software projects span huge teams, groups of 100 or more people, and there are implications. You really can't take a problem that is, well, I'll give a good example here. So whether or not a task can be partitioned between people can be kind of illustrated in this case. So a baby takes approximately 9 months to gestate, but no amount of engineering or project management skill is going to allow that baby to be delivered in 1 month by 9 women. So this is a kind of an absurd example in a sense compared to software engineering tasks, but this sequential nature of certain processes is fundamental to whether tasks can be divided among many people. And debugging typically has this effect. You find a problem, and it has implications for the rest of the program, and so you have to spread out the side effects of the fix to many parts of the process. So there's 4 types of task partitionability, and here so you have an unpartitionable task like pregnancy. So 9 months, no matter what, doesn't matter how many people you add to this process. You can add a completely supportive environment and all of the support in the world. It's still going to be a 9-month task. It's essentially a flat graph. Perfectly partitionable tasks are things where there's no need for coordination or communication between the people, and you can spread out the work to a number of people, and basically the amount of time it takes is equivalent to how many people you add, essentially. Tasks with dependencies requiring communication, which is pretty common in real projects. These partitionable tasks typically have they're not asymptotic to 0. You typically have a baseline where you can't actually improve beyond, because the communication costs tend to outweigh the development costs as you move as you add more and more people to the task. And there are worst cases where you have tasks with really complex dependencies, where the more people you add, the slower the project actually becomes. And it's actually typically not clear on this right-hand side that which of these 2 cases you're in. On the left-hand side, it's a little bit more obvious, but still wishful thinking can get you into a situation where you hope for a perfectly partitionable task, and in fact, it's actually partitionable with communication, which means that you can't add people to improve the schedule, which typically leads to Brooks' law. Adding manpower to a late software project makes it later, and there's various reasons why he discusses in his book about why this is the case. This is ignore this, the Brooks law at your peril if you're involved in a software project. So an attempt to try and address this issue is the discipline of project management. And so here we have, it's defined by Wikipedia as the discipline of initiating, planning, executing, and controlling, and closing the work of a team to achieve specific goals and meet specific success criteria. This isn't actually a discipline that's entirely, software project management specific. In principle, most of the project management activities were actually pioneered in construction projects and other places. And so in many cases, there's an attempt to try to use what worked there and to translate that to software engineering. But there are reasons why this is problematic. But in the traditional approach, we have this phased development where you have initiation, you have planning and design, you have execution and construction, monitoring and controlling of systems, and some completion and finish point where you close the project. This is often called the waterfall approach, and it works well for small defined projects or projects where you are essentially doing something that is mostly extremely well understood. As projects get bigger, so do the processes. So the discipline expanded over the 80s and 90s and provided some refinements of these traditional models. Prince 2 is one example, the rational unified process is another. These are tailored primarily to software engineering, but they get applied to other places as well. They're usually characterized by quite heavyweight processes, expert practitioners, and complex jargon. You can see to the right the Prince process model, which is almost as complicated as a software specification itself. But I mean, on some level, this is what you get when you allow software engineers to design processes for people. This all seems very sensible. You want to break down complex problems into simpler ones. You want to design before building anything so you don't waste money. And experts know best. What could go wrong, right? So what can go wrong is that, well, here, I'll give you a proof by analogy. So you have some visionary person who comes forward and says, people love scuba diving and people love unicorns, so we want to build an underwater unicorn. That will be insanely great. It will be the most innovative thing ever. Everybody loves this kind of thing. So let's do this. We're going to build an entire company around this. We're going to go IPO in 5 years, and so let's get started. And so you go and you get your angel investors, and they bring you a whole bunch of money, and you get a nice fancy office and expensive office furniture, and you start building your project like this. So this is what you're going to build. You're going to build an underwater unicorn, and it's faithful to the initial specification. So I mean, this is where, you know what, we at this company, we love underwater unicorns. We want to really own this. So we're going to be faithful to the original specification. And you know what? It's actually mostly like a horse. So this is a well-understood animal. This is as a design problem. This is really actually quite good. They have a well-defined methodology. Unicorn horns do have magical powers, so we can take advantage of that, and everybody understands this. So I mean, when it comes to marketing our underwater unicorns, we're going to have no problems whatsoever. So this project is going to be no problem, right? Well, unfortunately, what was actually needed was this. They're called narwhals. They're an Arctic whale. The horn is a specialized tooth. They're insanely cool. They have their own subreddit, so there's a whole subculture devoted to extolling the virtues of narwhals. But that's not actually what we were trying to build. And this is kind of meant to highlight that you can potentially have a clear idea from the outset, but there's actually, it's incompletely specified. And so this, as Rodney Brooks says, the incompleteness and inconsistencies of our ideas become clear only during implementation. And so this is a key insight that actually led to something called the Agile Manifesto. Now, this was a refinement of software practitioners who were kind of fed up with these heavyweight processes, who wanted to approach things a little bit differently. So what they favor in general, this is the Agile Manifesto here, individuals and interactions over processes and tools, working software over comprehensive documentation, customer collaboration over contract negotiation, and responding to change over following a plan. Now, obviously, when you say over, it implies that you're still doing these things. So there is still processes, there is still tools, there's still comprehensive documentation, there's still contracts, and there's still a plan. But it's a question of prioritization in this sense. And it's also it's a bit of a Zen koan to try and give you some, to make you think about the process a little bit. And as I said before, it was developed in response to increasingly complex project management methodologies that many of the practitioners on the ground were finding weren't actually serving them in delivering better software. I'm not going to get too much into the details of these, but I'll just describe a few examples of Agile software. We have Scrum, which is characterized by very short iterations, 1 to 4 weeks. Well-defined team roles and meetings. Each iteration delivers a functioning product. So in this sense, here the attempt is to try and take all of those 11 steps that I described for software engineering back at the beginning of the presentation and to compress them into a 1 to 4 week time frame. This has an impact on what you can actually do in that time frame, and it has an impact on how you actually specify your work inside the team. What I would say about all of these methodologies is actually that often you'll mix and match techniques between the two if you're an Agile practitioner. And you need to consider very carefully your problem space because it's very unlikely that any of these unmodified will be appropriate for you. And you need to consider the capabilities of your team and the reality of your work environment. Another approach is something called extreme programming. This extols the virtues of pair programming, which seems a little bit counterintuitive. Typically what happens in pair programming is you have two programmers who actually sit together and work on one piece of code. So you would think, okay, on some level this is going to be half as productive as if I put each programmer on their own piece of code. But in practice, pair programming dramatically reduces error rates and programming time because you have this sort of immediate editing process happening. One person writes and one person reads, and you sort of coach each other. And research shows that pair programming reduces error rates quite heavily, and it's quite popular in many, let's say, failure intolerant environments. Heavy use of automation and investment in improving underlying code quality is also a characteristic of extreme programming. Kanban is another example. This is based in concepts adopted from lean manufacturing, and it tries to balance demands for features with an explicit definition of team capacity. But the idea here is that all of these actually try to break down and focus the daily work of a programmer on more well-defined problems to try not to overload them with let's say, unreasonable objectives, and to try and keep the work that needs to be done something that can be completed in a fairly short term. And this is quite important to being able to produce a good estimate for that short-term work. And it's also important to maintaining the morale of the team, which obviously has a knock-on effect for the productivity of the team. With this, I'm going to segue into some conclusions about this. So we've taken a look a little bit at the discipline of software development, and explaining an idea to a computer is something that the human brain is not well equipped to do. So we have complexity, we have optimism, we have incompleteness of the original concept. Really, each of these is a variation on the original theme. Humans don't think like computers. And so what is kind of interesting about this is that typically good programmers have actually trained themselves to think a little bit more like computers. And so it cannot be understated that good programmers will make a huge difference to the success of your software project. So you want to get the right person for your software project if you are setting up a team to do this. Hiring software engineers is a special challenge in its own right, but it cannot be understated that good programmers can be almost an order of magnitude more productive than those who are not good. Project management. So I have 2 slides that summarize project management here. To summarize project management in 2 points, it's important to respect what the so-called iron triangle or the iron constraints. And what this actually means is that the constraints in this case are something that is delivered fast in terms of implementation time, something that is good in terms of implementation quality, and something that is cheap in terms of implementation cost. And the reality is that you can pick 2 targets, or you can prioritize 2 targets. You can have fast and cheap, but you'll get something of low quality. You'll have cheap and good, which will be a long implementation, and you have good and fast, which will be expensive. And in my own opinion, good and fast will be expensive and also risky. So project management, the second set of conclusions here I would say about project management is that good project managers typically have to make hard decisions to ensure project success. This is important to note for someone who's maybe not a project management practitioner, but somebody who's interacting with project managements. These project managers will typically have to be very conservative in their initial feature sets. They should, in my opinion, be favoring iterative development with fewer long-term commitments if possible. Many projects don't allow this, so this has to be balanced against the project realities. Reductions in feature scope are typically the way to reduce schedule. So if you have to deliver something sooner, or you're starting to go long in terms of your schedule, the only real solution is to reduce the amount of features that you're going to try and deliver. As we saw before, partitionability of tasks can really affect how feasible it is to add people to the task to reduce the schedule. Now, the final note I would try to leave you with is that the practices that are going to generate the best results in terms of achieving your overall project goals, I'm assuming that in this case software development is only a part of your project, are those practices which will allow you to validate your code, design and product strategy with customers as often and as deeply as possible. This is the best case scenario. And again, here you're stuck balancing the realities of your problem and your project with the desire to have a continual stream of feedback from the validation processes. And so I think it's important to try and keep this in mind as you go forward and interact with software developers, interact with project managers, and try to make software a valuable tool for your activities.